Alright guys, welcome to the third video of the AAQ Unit 2 Chemistry. In this video we're going to take a slight diversion away from the booklet pages. You can see that here's going to be on page 12, and what I'm going to ask you to do is make sure you've got some notes and paper ready for this, because you are going to have to take some notes and we're going to be referring back to this quite a lot throughout the course. What I'm going to cover is something we use called location CARs, and it's an incredible technique for you to be able to analyze trends across the periodic table. And when I mean trends, I mean as we go across a period or down a group, how do these things change? The way that we use this location CARs is this abbreviation where we have C for our nuclear charge, A's for nuclear attraction, R's for radius, and S is for shielding. And you can see here, I've got some of the more key terms here that break those things down, but I will be referring to these terms, so just make sure you have a read of them. Let's explain what we're having a look at here first, before I give you some examples of how to use location CARs. Remember, this could be worth anywhere between 4 and 10 marks in your exam. So being able to do this skill alone is going to cover a lot of the chemistry, and it's going to net you a lot of marks if you can do this effectively. So let's have a look at how we apply this. So when we look at sodium and magnesium, we're looking at two different elements that are next to each other in the periodic table. Sodium has a proton number of 11, magnesium has a proton number of 12. Magnesium has more protons than sodium, so therefore, magnesium has a greater nuclear attraction than sodium. So charge, it has a greater nuclear charge. Let me explain that a little bit more. So you can see here that sodium has all the protons in here, it's got 11, and it's attracting, we're talking about this electron right here, its ability to attract that electron. This has a 12, effectively, to attract this one. Magnesium's got a greater charge, it can more strongly attract that outer electron. A is what we refer to attraction. So there are 2 points I essentially covered there. One is the nuclear charge is greater, so therefore the attraction from the nucleus to the outer electron is also greater. This example shows us something to do with radius. So for our atomic radius, what we're looking at is the distance between an electron and the nucleus, or the outer electron and the nucleus. The further away it is, the more rapidly that attraction begins to drop off. Let's have a look at this example right here. So you can see here's the nucleus, and here's that outer electron. We're only going to look at one of them, you don't need to look at both. So you can see here, they're basically right next to each other. The attraction is going to be very, very high. The radius is very, very small. When we're looking at this example, you've got to go through another shell in order to reach that outer electron. It's much further away, therefore there is less attraction. And that's how we're going to link that atomic radius. Shielding, also known as screening, is to do with the number of electrons in between the outer electrons and the nucleus. Typically we're referring to shells, but it can get a little bit more specific when we talk about subshells later on. But mostly we're talking about the number of those big shells. As you can see here, nucleus to electron, there's no shielding, there's no shells in the middle of it. It's a straight attraction to that, so there's nothing blocking that. When you look at this one, the nucleus to the outer electron, there is actually one extra shell in the way. That means there's going to be less attraction to that outer electron. It's much harder for that nucleus to attract the outer electron. So whenever I talk about shielding, we're talking about the number of shells that we get added to it. And don't worry, I'm going to keep the key terms as we go through it. Now, some of the key examples that we usually see tend to be 4 markers, and they'll ask things about how does ionization energy trend across a group or down across a period or down a group. Same for radius, same for attracting a bonding pair of electrons, known as electronegativity, but we'll cover that later. CARs can give you the answer to all of these things very, very quickly. Let's go through some examples step by step. So I mentioned ionization energy, and this is something I'm going to cover a little bit more in the next video, but to give you some context, this is page 11, and I will cover this in the next video. But ionization energy is how much energy does it take to get this electron kicked off? How hard is it to remove that outer electron when it's being attracted by this nucleus right here? So this thing over here is attracting that one right there. How much energy do I need to come in and kick that guy out? Obviously, it's going to be much harder to kick this guy out than this one because you can see it's further away, there's more shielding, but let's talk about that now. So let's go down. And across a period. So I've gone across a period, I've gone from lithium, beryllium, boron, carbon, so I'm going this way across our periodic table. Now I've already written it out, so you can just copy these notes, but let me take you through them step by step. As I go from lithium to neon, you can see that their nuclear charge increases from 3 to 10. So I go from 3 to 10, nuclear charge increases, the proton number increases. That's how I would write that. And I would say, I would do this to make my life easier. Charge goes up. If my nuclear charge goes up, my attraction also goes up. So the attraction between the outer electron and the nucleus increases. Let's go to the next point. Now, radius. All of these aren't to scale, and you can see they're basically the same size, but there is a bit more nuance to that. If the attraction between this nucleus and this outer electron increases, I'd like you to imagine that this electron is being more strongly pulled in as that charge increases. So over here, I've got 3 protons in there. That was the worst 3 I've ever done in my life. Let's do it again, 3. And over here, I've got 10 protons in this nucleus. As you can see, 10 is far more protons than lithium. So that effective charge is therefore pulling this electron really close to this center. It's going to pull it right in. If it pulls it right in, it's going to shrink the radius of that atom. So the radius, let's do this in blue, decreases. And the way that I'm going to word this is the radius decreases as the outer electrons are more strongly attracted, so therefore being pulled closer to that nucleus. And then the final point over here is shielding. There is no difference in shielding, and we can show you this because if you go from lithium to neon, you can see there's the shells, one here, and you can see that that is the same across the whole lot. We're just adding more electrons to those shells. So there's no effective change in the shielding. Now, the question's asking about ionization energy. We've identified and analysed the trend. Now we need to give our summary. So this is like in maths where we show our working out and then we have our final answer. Only you get all the marks for this and you get all the marks for this. So there's about 4 marks effectively for you. The very final point needs to relate back to ionization energy. This is how I would summarize it. So the nuclear charge increases as the number of protons increase. Therefore, the attraction from the outer electron to the proton increases. This decreases the radius as the electrons are now closer to the nucleus as they're being more pulled strongly. Therefore, the energy required to remove the outer electron increases as there is more attraction to the nucleus, or there is more attraction to the outer electron. This bit's the really important part. So it's harder for me to remove that outer electron. Let's have a look at another example. Down a group. So what I've done here to try and make this a bit more visually easier to look at is we're looking at lithium going down to sodium, going down to potassium. Already you can see that potassium's much larger than lithium. So you can see where this is going to go. I've already written it out, but let's talk about it. So as I go down a group, this is where things change. This is when the location cars comes in. Location cars across a period, it's okay, we start along the top. So we go across and we go down from C to A to R to S. When we're going down a group for location cars, I would like us to start at the bottom. So for the location, we're going down a group, so we start with shielding. That's the bit we need to use to make our lives easier. You could write S-R-A-C as well if you really wanted to, but I think it's just really weird. So I just write C-A-R-S, and then I start here down at the bottom with shielding. Let's talk about shielding. It's very obvious that as I go from lithium to potassium, the number of shells increases. You can see here with lithium, I've got 2. With sodium, I have 3. And with potassium, I have 4. The number of shells increases. So the shielding increases as you go down the group. Big up. Radius. As I go down the group, you can see that the radius increases. And this is because we're adding more shells to the atoms. So that increases. Now let's think about the attraction. What we're talking about is this outer electron to this nucleus. This nucleus to this outer electron, and this one to this outer electron. As you can see, the attraction between that is actually decreased. And it decreases because the distance from the outer electron to the nucleus has massively increased. And remember before, the further away it is, the more sharply that attraction drops off. So it's much, much further away now, so the attraction drops off really, really quickly. The nuclear charge, what I'm going to do here is just like last time, I'm going to do a little bit of a squiggle, but it does increase. I'm going to write it there. So the nuclear charge does increase as we go down, because if we go down from there, lithium has a proton number of 3, sodium has a proton number of 11, potassium has a proton number of 19. So go from 3, 11 to 19, which is a dramatic increase of nuclear charge, but that's still not enough to overcome the distance from the protons in the nucleus to the outer electron, which is why I think it's important to start at the bottom and work our way up. You don't even need to write one for C, but the way that I've done it here for you is the nuclear charge does increase, but not enough to outweigh the other factors. Now we've done our analysis, we're going to then write our summary, and this is where we actually get our marks. We're talking about ionization energy, so as I go down a group, how does that affect my ability to kick out the furthest electron? Remember, as I go down, my attraction actually decreases. So it's actually easier for me to kick off that outer electron because it's so far away now. This is how I'd write this. So the nuclear charge, let's start from S. So the shielding increases as you go down a group. The radius, therefore, also increases as more shells are added, and this means the attraction decreases as the distance from the outer electrons and nucleus increases. Therefore, the energy required to remove an outer electron decreases as the electron is much further away from the nucleus and therefore less attraction. And here you can say due to shielding if you want to repeat yourself. You can do this in bullet points. This is how I would write it in an exam, with the C, the A, the R, the S, the arrows, and the summary words, and then the therefore. It doesn't need to be full sentences. Bullet points works. To make your life easier, this is the skill we need. Now that talks about ionization energy. Now, I'm going to do the same again, but this time we're going to look at radius as being the question. How does radius change? How does radius change as we go across the period? How does radius change as we go down the group? We're going to use cars to be able to summarize and answer that. This one's a little bit easier, so I'm going to take a little bit less time on it, and I'm going to break it down a little bit more quickly. So for radius, as we go across the period, let's do this like this. As you go across the period, what happens? Location cars, we're going across, we start from the top. C, the charge increases. Great. If the charge increases, so does the attraction from the nucleus to the outer electron, goes up. R, the radius. If my attraction goes up, it means I'm more strongly pulling those outer electrons closer to the nucleus, so therefore this decreases. My radius decreases. I'm not increasing any shells. This is all going to be in the same shell. We're just adding electrons to the same shells. Therefore, this is where we go back to that radius. Across the period, the radius will decrease. This is because the charge across a period increases as the nuclear charge increases. This increases the attraction from the nucleus to the outer electron, and therefore, there's our answer, therefore the radius from the distance between the nucleus to the outer electron decreases as you go across the period. Tick. This is likely to be a 3 marker. Down a group, let's do the same analysis. We're going down a group, so this time we're going to start at S. Let's have a look at this. Lithium, sodium, potassium. As I go down the group, the number of shells increases, the shielding increases. This increases the radius because I'm adding more shells, so therefore my atoms are getting bigger. However, my attraction decreases because now the nucleus is much further away from that outer electron. So my attraction between the nucleus and the outer electron decreases. The question is about radius. Let's link it back. Therefore, as we go down a group, the radius will increase. This is because as we go down a group, the number of shielding increases as we increase the number of shells. The attraction decreases as the outer electron is now further away from the nucleus, so there is less attraction. Therefore, the radius of the atoms going down a group will increase. Full stop, there's your 3 marks. And that is how you use location cars. I've got one last example. This time we're going to look at attracting electrons. This is also going to be known to you guys as electronegativity, the tendency to attract a bonding pair of electrons. So this time what we're looking at is we've got 2 imaginary electrons. Imagine this guy here and this guy right here. And they belong to some other dude. And I want to attract these to this. The only thing that's going to attract me to this is that nucleus. So we care about that nuclear charge. It needs to be higher in order for me to attract them in. That's what we're looking at. So across a period, I'm going to do this one really, really quickly. You guys can write the full summaries because I'm lazy. And we're going to go across a period. So if we go across a period, we're going to start from the top. Charge increases. The nuclear charge increases as the proton number increases. Therefore, the attraction increases. The ability to attract the outer electron from that nucleus increases with a higher proton charge. The radius decreases. This is because there is more attraction from the outer electron to the nucleus, so therefore it pulls those electrons in. Shielding stays the same. Right, we've done our analysis. Let's very, very quickly look at the therefore. we want to know what's the trend for our electronegativity as we go across the group. So does it increase, does it decrease? What we're looking for is, as we go across, is it easier to attract electrons? We've said attraction goes up. So yes it does. This is how we would summarize it. As we go across a period, the ability to attract, or the tendency to attract a bonding pair of electrons increases. This is because the nuclear charge increases as the proton number increases. The radius decreases as the distance between the nucleus and the outer electron also decreases, as there is a stronger pull from those outer electrons to that nucleus. And finally, the ability to attract a bonding pair of electrons increases as the nuclear charge is also increased. Therefore, the electronegativity will increase as you go across the period. So that's how you need to summarize everything together. You guys can do the same for going down a group. I think you're sick of me saying the same thing over and over and over again, but you can generally tend to see the trend now. But we're going to use location cars a lot through the course. I'm just going to keep referring back to it when we need to talk about any form of trends. So we'll just say location cars, and then you do your analysis, and then you answer your question. And that's the routine we're going to use in order to solve these periodic questions. Right, guys, this has been a long video. Hopefully you've made some notes. You will be coming back to this video more than once. I'm sorry, but you will. And hopefully it's going to help you out for the next few questions. Right, guys, I'll see you soon.